Hollywood. Here we go. Um, thank you, thank you. Um, can you all see the board? Is it? Let me switch to something more visible. Is the lighting okay in here? Well, we're dealing with COVID, so we're trying and learning new things as we go. Um, Classrooms in warehouses and lab environments is new to all of us. So, um, in our last theory talk, for those of you who were, how many of you were in pod 2 when we talked about electric theory? Show of hands. Okay, majority of you. We talked about some of the basics, and we'll review the highlights of that talk before we dig into actual circuits, and we talk about voltage drop, Ohm's law, and electric power today. So if you recall, we started our talks by looking at where electricity comes from, right? And we looked into a hydrogen atom, which is the simplest atom in the world, because it's made up of only an electron, a proton, and a neutron. And we talked about how neutrons and protons are bound together in the nucleus of atom, kind of like water and land on Earth. And electrons are flying around, and that's why electrons are most valuable electric charge quantity to us, because they move, they can easily move. Protons and electrons have the exact same charge. Protons are positive, electrons are negative, but protons are bound in the nucleus, so they're land bound, kind of on Earth, but electrons are the ones that move. So electricity, when we talk about electricity, we're usually talking about movement of electrons. Everything in the world is made up of the same quantities, it's just different numbers. So you have a bigger landmass, more water in the nucleus, and then more electrons flying around, and you'll have a different matter. Could be oxygen, helium, whatever you look at. We also talked about how when matter or different items come in contact, electrons can move from one to the other. And when we build up, we have excess of electrons, then we have a negatively charged object. And when an item loses electrons, we have a positively charged object. And these were the two important rules that led into how we get work done with electricity, right? We had that example. We said that if you use an old school comb, the plastic ones, everything, we said that under normal condition has the same number of electrons and protons, so have a balanced charge, right? There is neutral, there is no excess of charge. What happens when you comb your hair with an old school plastic comb? It starts picking up electrons from your hair. So after a while, you have a negative charge build up on that comb. And if you get that comb close to a piece of paper, it'll start, based on the two major rules of electricity, where opposite charges attract and negative similar charges repel, the excess electrons on the comb will attract the positive, the protons of your piece of paper, and it kind of attaches to it. You can do this experiment. You can do it with a plastic pen and a piece of paper. It's pretty simple. You put on a magic show for your kids, nieces, nephews, whoever. If you have kids around, they love to see things like that. But this is the basis of our entire industry, how we do work, right? Electricity, we can move things. Electric cars are a big hit right now. Tesla, soccer mom station wagon blows the doors off of Ferraris and Lamborghinis because of the amount of power that electricity can generate. So, but they all come from the same thing. When you have different charges, they attract each other. When you put similar charges, they push each other away. We also looked at batteries as to understand where voltage comes from, right? Like the definition of voltage. We already said that everything in the world, including your hard hats, your body, batteries, everything is made up of the same electrons, protons, and neutrons. And electrons, when they're contained in a space, they're kind of people in rooms during COVID, right? They push each other out to be equally distanced. Now, if you have a very big space, people would stand 10 feet apart, maybe as much room as they have. But if you pack them in a smaller space, they might be closer than 6 foot that we want them to be, but they're still equally distant from each other. Now, battery is a special device. There's a chemical reaction going on inside the battery that pushes the electrons, majority of the electrons, to one end of that device. Is that the positive or negative terminal? Negative. That's why you see on all the batteries that you use, your car battery, your AA battery, there's always a plus and minus sign. That's what it's telling you. More electrons on the negative end. So what happened when we hooked up a piece of wire across that battery? Electrons start moving through that piece of wire, right? The concentration of because the wire, a metallic, copper, aluminum, whatever you're looking at, it has mobile electrons in it. So it's got millions and millions of electrons sitting. As soon as you hook it up here, the excess of electrons in the battery start pushing all those electrons through the wire. So we get movement of electrons, and the electrons go all the way to the other side of the battery, the positive terminal, and then inside, as soon as they enter, they get pushed to the negative terminal again by that chemical reaction. So this keeps on going. This is what we call direct current. Why do we call it direct current? It's always one direction, right? It's always negative to positive. So moving things like that in one direction is not what we always do. Imagine if we were to flip the battery, right, at a certain rate. Keep turning it upside down. Look what happens to the direction of current, right? It keeps flipping with because the negatives always are pushing. So if negatives are down here, your negative terminal, it pushes the electrons one way. When you flip it, it goes the other way. And it gets work done. That's alternating current. I don't know if you can see the title on that page. Seems like our resolution is a little bit off. But that's alternating current. That's the basis of what we do, right? Our 12240 systems, we'll see it in more detail, is based on alternating current. But they both do work the same way. We looked at how AC, the analogy that we used was AC is kind of like a reciprocating saw, right? If you look at the blade on a saw, it's got teeth going both ways because it cuts going forward and it cuts coming back. But on a bandsaw, where you see on this side, the blades are unidirectional. It only cuts in one direction. That's similar to DC. They're always moving. Which way do you think the blades cut? Going down or up? Down. Why would it cut downwards? You don't want the piece to fly up. So it always cuts going downwards. And that's similar. Now, which one does more work? They both do work. It depends on the design, the power, and all that. But you can cut through things in both ways. Same thing we can do electrical work with DC or AC. Next topic that we covered in our part 2 was resistance, right? Resistance is defined. Electric resistance is defined as opposition to movement of electrons. We said electrons want to move through the wire. There is friction that resists that. Now, this resistance is the basis of most of our work in terms that it allows us to control electrical usage and also work safely. And the primary two terms that come out of resistance are insulators and conductors. So what's an example of an insulator, Myrna? Well, electric insulation. You all did safety class, right? Right, the rubber coating on the Romex is an example. What else? What did they tell you to use during your safety class the most? Huh? Gloves, PPE, right? Even your hard hat, it's electric rated. So it protects you. You see some of these old school guys that have those aluminum hard hats from 1950s. They think they're all that. Very stupid, because if you come in contact with a live wire or a pipe that's energized, you get a shock right into the head. So these are all electrically rated hard hats. But yeah, those are a good example. Is air an insulator or a conductor? Is it an insulator? Always? Not always. So air is an insulator in general because, you know, you all are sitting here and we have 120 volt outlets next to you, right? I don't see Daniel getting a shock every few seconds, right? It's basically you got your separation by air, because this room is filled with air, but electricity not traveling through it. But then we talked about lightning, right? An electrically charged cloud discharges to the ground through air, right? So in some cases, air becomes a conductor. That's when arc happens. That's why when it's the air is moist, we see more conductivity. So, and this is another one, touching back on safety. This is why you got to be aware as an electrician of, what the system is, what the voltage is that you're working on. Because yes, air is an insulator when we're dealing with 120, 240. But at 480, 600, 1,000, 2,000 volts, that changes. This is why in many cases we have to label equipment on the PPE that's required to work on those systems, because once you put enough voltage, put enough electrons that they want to jump through the air, they will. And if your body is the closest thing that they can jump through the air and catch, they'll go through you. And the energy of arcs, electric arcs are 4 times hotter than the surface of the sun. So people evaporize when they come in contact with high voltage. That's why it's on us to make sure everything is labeled when we install equipment. Now, in Resi, we're dealing most of the time with standard system. For those of you that go on to multifamily, we do have high current, 3-phase system, multi-voltage levels, but in industrial, this becomes a major issue. Conductor, what's an example of a conductor? Copper is a good example. Most metals are good conductors. Copper is one of the best. When we talked about conductors and resistance, we compared our wires to piping system, right? So first thing that we talked about is AWG. What does AWG stands for? Wire gauge. So what does it tell you? What is a wire gauge? When we say size, are you talking about length? Are you talking about cross-section? What are we talking about? Cross-section. Cross-sectional area. It's telling us, because length, we change it, right? You can have 10-foot 12 gauge, or you can have 1,000-foot 12 gauge, right? So it's talking about the gauge of the wire, much like a gun, right? When you go shooting, you have a 12-gauge shotgun. It's telling you what's the gauge or the cross-section of that wire. Wire gauge and resistance is similar to piping and resistance, right? As we go through piping, you increase the pipe size. So a 2-inch pipe has less resistance than a 1/4-inch or 1/2-inch pipe, right? As you increase the gauge, resistance of the pipe to fluid movement goes down. This is the resistance of fluid, pipe to fluid is why, when you're talking about pipes in a home, in a residential construction, there is not much resistance. But if you're thinking about moving crude oil from Canada to Houston, Port of Houston, then that's a long distance. So resistance matters. So we'll get there. But gauge, so we're talking about cross-section. So this is a higher gauge pipe than this one. Same thing. For our 1/0 is a higher gauge than 14 gauge. So 12 gauge is a higher gauge, means it's got a bigger cross section. But why do we use the numbers differently? Let's go back and look at this. So a 14 gauge, we're using a higher number than 12 gauge. Why? Even though it's a smaller wire. Why do we use a bigger number? As an electrician, it's a reminder to you that 14 gauge has higher resistance than 12 gauge because it's inversely proportional, right? The bigger the cross section, the lower the resistance. So the lower the number that we see there. So keep that in mind. Length. We talked about oil going through pipelines from Canada to Port of Houston. That length adds resistance. So we have to put pumps or something for fluid to go through pipes. Same thing for our wires. As the length of the wire goes longer, resistance goes up. Now again, we're doing wiring a house, 100, 200 foot long circuits tops. We don't care about that resistance as much. But if you are going 1,000 foot, you have a custom home with a garage that's 1,000 foot away from the house and the other side of the property, then we have to worry about that. And we'll talk about voltage drop shortly in this lecture, so you'll see where that comes from. That's where our similarities to plumbing and pipes end. So for us, material matters, right? Now, you've done part 2, so you're all code expert. Let's actually look. What is this table? Do you remember what this table is? 310.16? It's probably the most used table out of the entire NEC. We call it the ampacity chart or table. It tells us what kind of a current we can put on each size wire, right? Now, regardless of what table, almost every table in the NEC book, they separate copper and aluminum. So when you look at your tables, like this is the ampacity chart. If you go to 310.16 in your book, you see the first 3 columns are for copper. The next 3 are for aluminum or copper-clad aluminum. How much current can be put on a 14 gauge wire? Who knows? If you were to guess, you guys are new, you'll know this like back of your hand in a few weeks, but do you know how much current you can put on a 14 gauge wire? 15. Is that for copper or aluminum? Copper. This table tells you that, right? So if you look at 14 gauge, the first column is showing you the gauge of the wire. Next one, and 60 degrees C insulation is what we look at for Romex, the wire that we use the most, the jacketed wires. It tells you 15 amps is what you can put on it. Now, what is it for aluminum? So on a 14 gauge aluminum, how much ampacity can you put? It's a dash, right? What's that telling you? You can't use 14 gauge aluminum. So resistance is that important. Marina, how much ampacity can you put on a 14 gauge aluminum? None. You can't use it. The code doesn't allow you because it's got higher resistance than copper. Now, I guarantee you, maybe 99 out of 100 electricians out there, if you go and ask them that question, they'll go blank. Why is this a dash? Why am I not allowed to put 15 amp? Why can't I use 14 gauge aluminum? But you know it now. So George mentioned that this is a very special school, and he's right. This is not the norm in our industry. You guys are being trained here to be in the top 1% of electricians out there. So take advantage of these opportunities. Don't take it lightly. Don't just sit here because, I got to go through this because it's part of my training. This is a very unique opportunity. You can become a very, very specialized person by using the utilities and the facilities that we have here. So resistance for us is a big thing. And aluminum is a good conductor, but copper is better. And you see that how they're separated. Next item that we talked about was temperature. For a plumber, and we're not talking about breakdown temperature when we had the freeze last winter that all the pipes busted. We're talking about normal operating temperatures. For a water pipe, it doesn't matter if the ambient temperature out there is 35 degrees, it's cold day in winter, or if it's 130 degrees in an attic in the middle of a summer. Water flows the same way. The resistance of the pipe doesn't change much. But for us, that makes a big difference. And you'll see this when you do your wireman test. I'm pretty sure George does some problems for you on this table. This is what we call ambient temperature correction factor. So normal ambient temperature in US cities, most of the US cities, is 78 to 86 degrees. Houston, San Antonio, Phoenix, they all fall under this. So our normal ambient temperature is between 78 and 86. Northern cities too. This is a pretty wide range. This is the average for the whole year. When you look at let's go back to the 60 degrees C. So Romex falls under that one for us. So look, it says your correction factor is 1. 1 means there's no correction. You multiply something by 1, it's the same thing, right? Nothing changes. What it's telling us that if you're in this range, the ampacities that you saw in the last table, 310, 16, is what you use. But what happens if the ambient temperature is higher? Let's say in Phoenix, Arizona, we have a city that tells you, hey, we consider attic ambient temperature in Phoenix to be 96 to 104 degrees on average per year. So the ambient temperature. You can't use the numbers that are in the 310, 16 anymore. You have to take that number and multiply it for Romex by 0.82. 0.82 means if you, on a 12 gauge, 310, 16 tells us we can put 20 amps on a 12 gauge Romex. When you multiply 20 by 0.8, it gives you 16. So in an attic in Phoenix, when they're telling you they're following ambient temperatures higher, you can only put 16 amps on that wire. So if you have a water heater that's rated that needs a 20 amp circuit, you can't wire it with the 12 gauge anymore. You have to upsize your wire to 10 gauge. So these are concepts that as an electrician, now you guys are new, you're just starting. So this is a primer for you to see what's to come. You'll learn about these down the road. But I want you to understand that all of this is because temperature increases resistance. So your 12 gauge copper wire that was rated for 20 amps in a hot environment at a chemical plant or an attic in Arizona is no longer considered 20 amps because its resistance jumped up. So you can use it, but it'll give you the same ampacity as a, let's say, 14 gauge in that environment. So as electricians, you got to constantly look and think outside the box. Our trade is a little different, right? When you look at HVAC, plumbing, they're physical quantities. They can see and feel the airflow, water flow. If there's a break in the pipes, they see leakage. We don't see electrons moving. So you all are in a special group, a special class. You got to start thinking, putting things together to get the big picture. So stop me if you have any questions. Normally when I don't see any questions, you either grasping everything that we talk about or nothing. So I hope it's the former rather than the latter. But so we got to worry about temperature. That was the last item on our 4-item list there. So the gauge of the wire, cross section, determines resistance and ampacity. Length of the wire is an important factor. Material copper versus aluminum, and temperature. All right, last concept that we talked about in our Pod 2 theory lecture was we went over quantities and their units of measure, right? This example that we used was time. What's the time is a quantity we can measure. What's the unit of time? Second is the base unit, right? Then from seconds we build other units like minutes, hours, milliseconds. Same thing happens with our electric quantities, right? So the first one that we talked about, electric current, is a quantity we can measure. What's the unit of current? Huh? I is the symbol. What's the unit? Amps, right? So that's a good point. To show these quantities in equations, we use symbols. So for time, we use T. For current, we use I. For voltage, we use V or E. E is electromotive force, is another name for voltage. So on some of your charts, electrician charts, you might see E instead of V for voltage, but it's the same thing. And for resistance, we use symbol R. What's the unit of voltage? Volt. That's easy to remember. What's the unit of resistance? Ohms. How many ohms tells you how much resistance your system has. So today we're going to get into actual circuits. So we go back to the battery example. It's easier to see things in DC and then move into AC domain. But when we connected the battery by a piece of wire, now you understand resistance is the friction of the wire to movement of electrons. What you do if you do connect the two ends, we call that a short circuit in electrical terms, right? Short circuit means it's a very low resistance path that we've created. So we get a very high current, it heats up your wire, and usually if it's a battery, it kills the battery pretty quickly. You might see arcs flying. If you've ever tried to charge your car battery and accidentally touch the positive to the body or a negative terminal, you see a spark come out. That's examples of short. So we put a resistance in that path to control. Now it could be a resistance or a piece of equipment. Everything has resistance. In the flashlight circuit, we actually put a light bulb in that wire. And that becomes useful usage of electricity. So electrons are flowing through the light bulb much they were flowing through the wire, but light bulb, the old incandescent light bulbs, were actually a very high resistance designed to emit light when it got hot, so it would glow. And that's all. You ever tried to change an incandescent light bulb right after it turned off or went out? Burn your hand pretty quickly, right? It was hot. And that's because we were heating the tungsten in the element inside the light bulb, and that would glow and give us light. LEDs operate on a different, they're diode based, so they're semiconductor based, so they have a very different system. They don't get hot and they don't use as much electricity. But we're focusing on this right now. So we already talked about short circuit. Another term that I want you to remember is open circuit. So open circuit means if we break that wire, the conductor, or somewhere in the loop, if we break it, then it opens the circuit. It stops the flow of electrons. You were introducing an air gap. Myrna, is this a short circuit or an open circuit? It's an open. What's the example of a short circuit? When you connect this with a switch is basically a device designed to just switch between those two states. It's an open circuit right now. When you close it, it completes the loop, you get electrons. So it's almost like a bridge that goes up and down, right? All these little switches that you've been turning on and off your entire life, that's all they're doing. They're closing and opening your circuit. So those are two terms that I want you all to remember. Next concept, series and parallel confuses a lot of electricians. Now, you all have driven from Texas to Louisiana, I'm sure at one point. All the bridges that we have over the swamp, you finish one and then you go on another one, that's series. What it means is that, so here we're seeing two bridges, right? One bridge finishes and another one starts. If that bridge went down, could I get cars going through anymore? No, it'll stop the flow. If that was untouched, but this one went down, would I be able to get cars to go through? No. This is an example of series as opposed to parallel. So Brooklyn Bridge and Manhattan Bridge are right next to each other. That's an example of parallel. What happens if Brooklyn Bridge is shut down for repair or it goes down? No big deal, because we have another path. Cars will still be getting across that body of water, right? If this one went down, this one would still work. So this is an example of parallel. Now, let's look at our basic circuit. So if I had two light bulbs connected like this, where electrons would move from the battery, go through the first one, then the next one back to the battery, that's an example of a series connection of light bulbs. What happens if I take that light bulb out, if it's broken there? The other one goes off. Same thing, because electrons can no longer get through. It's the movement of electron that turns the light on. Now, if I take out the other one, it also kills the circuit, right? Because electrons cannot get through that portion. Parallel, remember, Brooklyn Bridge and Manhattan Bridge. So electrons come and they reach a fork. You have an option, right? When you have a parallel path, you can choose which path you want to take. So they split up. Some go through the first one, some go through the second one. They all have to come back together and go back to the source to keep the flow going. But if you take one of these light bulbs out, no big deal. The other one still works. If I take that one out, no big deal. This one still works, right? Which one of these two systems you prefer to have in your home? A system that when one light bulb burns, the whole house goes dark? Or the parallel that, they're independent? So this is why our AC systems, residential AC system, we're almost always using parallel circuits. We do use series in some cases. I actually had an experience just a couple of weeks ago. So my Christmas lights, I have multiple branches that fall off, and it's like a sectional, like one of those icicle looking all around the house. And all of a sudden, I noticed a big section of my Christmas lights has gone out. All I had to do was change one light bulb in one of the strings, and all the other ones came on. That told me that that section was on a series connection, because one light bulb going out shut down all the other ones. Now, considering that I had other parts of it that was still working, this is an example of what we call the series parallel circuit. Means you have a combination. And we won't get into the details, but and you won't see this on your wireman test, but if you ever do, I don't even think they give you series parallel in Journeyman. I think master level is when they start asking questions on those. But there is a possibility to have like one light in series with a few lights that are in parallel. And that's an example where the Christmas lights, that one section was working. But out of this, I want you to remember, anytime you hear the term series, think about swamp, going over the swamp on those bridges. Anytime you hear about parallel, think about New York. You got Brooklyn Bridge right next to Manhattan Bridge. All right. Do you know what size wire is this? 12 gauge. That's correct. Is it 12.2 or 12.3? 12.2. Why is it not 12.3? I see 3 conductors in there. Well, you only have one hot, you have one neutral, right, and one ground. So the two, but you're on the right track. The two, the hot and neutral, what are they called in the code book? Huh? They're all conductors. What do we call a hot conductor in the code book? You don't see the term hot. Ungrounded. And what's neutral? Grounded. What's ground? Equipment grounding conductor. So we're using different terminologies in the code book. You got to make sure you have both, because our subcontractors may not understand if you use the code language. And at the same time, when you're doing your test, you're not going to see hot or neutral. Usually it's grounded, ungrounded. But what we were talking about is that the two conductors, the ungrounded and grounded, or hot and neutral, the black and white, are current carrying conductors. Current carrying conductors. The ground, bare green wire, what we call it equipment grounding conductor in the code book, is not supposed to be carrying any current. It's a safety line. When it's carrying current, it's only to trip your breaker. It's because something went wrong. Something's wired wrong, something came in, a short circuit happened somewhere. Now you understand what a short circuit is. A short circuit happened that connected your hot and neutral or hot and ground together. And that's when this starts tripping the breakers. So because we have two current carrying conductors under normal conditions, the black and white, hot, neutral, ungrounded and grounded, we call it a 12-2. Now, I'm not going to show the equipment grounding conductor or the bare or green copper anymore, because that, is only a safety line when something goes wrong. So under normal condition, this is your electric circuit. And source of power is usually in our AC system is the service, right? Service comes to our panel, and each breaker becomes the source for that specific circuit. So here we got a 20 amp breaker connected using the two wires to the light bulb. This is a standard circuit that you have probably wired up already. Have you guys started wiring up in the lab? You did some work here? So, when you connect those two, it's similar to that flashlight circuit that we talked about. So you can have parallel, and this is how we do it properly, right? What happens when the electrons start moving? We have a 120 volt system that pushes electrons, much like the battery was pushing, and gets the electrons to flow through the light bulbs. Let's say switches are on. I'm not showing you switches here. But what's the switch? It's basically opening, closing each of those circuits. So when you have two lights on one switch, your switch is here, opening, closing this. When you have your lights on different switches, you have one switch here, one switch there. So if this one's open, it only turns this one off. So the concepts are very similar. It's just a different system that we're using. So the current, the electrons are flowing, they get to this junction, they split between the two, and then they go through them and come back to the other side. This is a very important point. The current in a parallel system splits, but the voltage that these devices see is exactly the voltage that was supplied. This is why we call this the system voltage, right? System voltage in our residential is usually 120, 240 in single family. In multifamily, we usually have multiples. You have 120, 240 for standard stuff. Then you might get a 120, 208 or 240, 460. There are different. If the three-phase comes in, we have multiple systems. But when we say system, it's because the voltage in our design is supposed to stay the same. We're not supposed to change the voltage. All the lights, all the fans, all the motors, everything that we use is designed to work either on 120 volts or 240 in a single family residential environment. If you put a different voltage on it, it either doesn't work or it might misfire. You don't know what's going to happen because it's not designed for that. Current, on the other hand, is the one that splits up. If you turn on more lights, what does your system do? Pulls more current from utility. That's why you have that meter, right? As soon as you start pulling, they start charging you. But it's designed to do that. Voltage is supposed to remain the same. Current, we can change it as we need. If you're traveling, current should be close to zero. You know, you can shut everything down and not pay anything. Now, this is an incorrect installation for residential, but we can do it. I've seen people by mistake do this, especially since you guys are learning now. You might actually wire up something like this. So this is in a series. Instead of all devices being parallel between the hot and neutral, one gets the hot and then feeds the other one. So we're taking Brooklyn and Manhattan Bridge and putting them kind of like in the swamp, back to back. And that's the wrong way of doing this. What happens here, the same current flows through both of them. But look at what happens to the voltage. You're splitting the voltage between those pieces of equipment. So if they're exact same light bulbs, they each get half of your voltage. If you have a 40 watt and 100 watt, they get different level voltages, depending on resistance. The higher resistance gets the highest voltage. So, take-home message from this slide is that our residential installations should be parallel. We have a system that's designed to work on 12240 volts. We want to keep it always the same, so we hook up everything in parallel. And in parallel circuits, voltage is kept the same, but the current is splits or usage of current changes. In series is the opposite. The current stays the same as it goes through the same size equipment, but the voltage changes, and that's a no-no for us. We have system design, so we don't want anything to get different. Now, with old incandescent light bulbs, if you accidentally wired your lighting circuit in series, you could tell because it would turn on dimmer than normal. So you knew, oh, there's something wrong. With LEDs, depending on their design, some of them don't turn on, some of them may turn on, blink, it depends. So you got to pay attention, close attention to how your wiring is done. Any questions thus far? Okay, good. Yeah, go ahead. Current carrying conductors, right. Yeah, remember, all conductors carry current. But when we say current carrying conductors, means under normal conditions. So the green or bare copper will carry current, but only if something went wrong. It's a safety line to trip your breaker. White and black, hot and neutral, ungrounded and grounded, whatever you call them, they're designed to carry current whenever you turn on equipment under normal working conditions. Go ahead. Well, again, that's why some of them are insulated, but the ground should, if you wire the system correctly, the ground should carry current for a split second. Breaker should trip and stop all voltages in that system. And, you know, odds of someone touching that wire while it's tripping, it's next to nothing. So that's why, you know, with ground, a lot of times it's just the bare copper. But the neutral, this is a common mistake that rookie electricians make. They think neutral doesn't carry current or has less current. Neutral is same as hot, right? Actually, let's look at our circuit here. So where do the electrons come into this circuit? On the negative or positive terminal here? On the negative? Anybody thinks they come in on positive? Nobody? Electrons, right? Electricity is flow of electrons for us, right? We don't move positive charge, so we're always moving negative charge. So in this circuit, would electrons come into the circuit from the negative, this side, or from up here? The black? How many think they come from the black? Show of hands. 1, 2, 3, 4, 5, 6. How many think they come from the white? 1, 2, 3, 4, 5. Split in half, and then I guess we have 5, 6 people that are sleeping or have no opinion. Actually, you're all wrong, even the ones that didn't comment, because they do come from both. Remember, what's the difference between DC and AC? In DC is direct. The negative is always feeding your circuit. In AC, it's constantly flipping. So your negative and positive is constantly flipping on your breaker. We show this just as a starting point. We say, okay, if your negative is here, it's going to show up as negative on there. But it's constantly flipping. Yes, go ahead. No, if you won't have a circuit if you don't have any return path. So if you don't have a neutral, you have another phase conductor, right? It's like a 240 system. Is that what you're thinking? If you only have one hot and nothing coming out, you don't have electricity flowing. Your circuit is not complete. So there's got to be a return path. Now, what you're saying, you see it in the field, because let's say you're wiring up a water heater or an AC unit. There's no neutral, no white. What happens is the two that you're bringing in, they're two hots or two ungrounded conductors. They're actually working in opposite phase. So when one is pushing, the other one's pulling. So that flipping is happening. It's just that it happens exactly the same time for both of them. You ever notice in the panel, you have two separate buses, right? And you bring the two hots, you drop them in. They're completely separate. If you short circuit them, you get a kabang. It's going to be fireworks, right? Because they're both 120. How do we get 240 between them? It's probably circuit theory 2 that we cover this, but they're flipping exactly opposite to each other. So when this one's positive, this one's negative. And then when this one goes negative, this one goes positive. So the difference between them is always 120 plus 120 gives you 240. But that's a little bit too advanced. What I want you to understand from today's lecture is that we don't have negative and positive here really, because it's constantly changing. So the negative and positive is determined by the power generation at the power plant, and is pushed all the way down through transformers to your through your service and here. So when we put one plus and minus on an AC circuit, we're only saying that this is a starting point. But your hot and neutral both bring in electricity. That's why there is this misconception that neutral is safer than hot. You should drop that very quickly, very early on. Go ahead. Mm-hmm. Right. That's a very good point, right? So let's say I take this out. This light bulb is out, right? Hot, everybody's scared of the black because you're like, oh, that's hot. Neutral, oh, it's connected to the ground at the service. That's not dangerous. Yes, it is. When this is out, if you put anything between this neutral and the ground, which includes your body, if you hold this and that switch is on, it delivers the exact same power as the other one. So it's never, it's not, even though we bring them together at the service, it doesn't mean they're doing the same thing. That's a good point. Any other questions, guys? All right. Huh? Yeah, well, in AC, neutral is the grounded. Negative keeps changing, right? Remember? You get both positive and negative. What positive and negative are telling you is which way your electrons are flowing, right? So think about your neutral in a proper circuit. Light is on. What happens is when it's negative is on the neutral, it pushes electrons into your circuit. When it flips, it pulls the new electrons out. Electricity flow doesn't change. Your light bulb doesn't go, off when it's moving this way, right? It's always on because it's the flow. Reciprocating saw, right? We got to keep going back to our example. You can cut your finger exactly the same way, whether the blade's going this way or that way. So in AC, it cuts both ways, and that's why neutral is dangerous. This is a good point to talk about this. We've talked about AC, how this flipping happens, kind of like we don't turn a battery to generate. We saw that, right? It's usually a magnetic field that generates. But let's think about that battery because it's easy to remember. If I'm flipping that battery to generate AC, how fast I flip is what we call the system frequency. What's the frequency of our 240, 120, 240 here in the US? How many hertz? 60 hertz. That's telling us that we're flipping that battery 60 times per second. In Europe, it's 50. So with our AC, that direction is changing 60 times per second. These are simple concepts, but I said it, 99% of our electricians don't know out there how these are working. And they read the code book, and it's a puzzle to them. They try to memorize it, and it's different. So understanding some of these basic concepts will take you'll be the go-to person on your team, and you can move up the ranks pretty quickly. Any other questions on the basic concepts we've talked about so far? Okay. Next thing that I want to talk about is voltage drop. We tapped into it when we were talking about resistance, right? And I said in a normal house, 100, 200 feet of wire, we usually don't worry about resistance of the wire. But if that garage is 1,000 foot away, it might impact your decision, and we'll see why. So this is because the wire, even copper, that's the best conductor, doesn't have zero resistance. It has a little bit of resistance. You're code experts. Table 8, chapter 9. Go to your table 8, and you'll see it tells you what the resistance of each of these conductors are. This is what you see in chapter 9, table 8, right? So look towards the right side, you have copper, and the copper that we use is uncoated. Coated copper is got like galvanized stuff on it for rust protection, but we use uncoated. So this is the column that we'll be looking at. Now on top of this, it says KFT. What's KFT? Huh? Well, K stands for what? Kilo. Kilo and FT is feet, kilo feet. So 1,000 foot. All it's telling you is 1,000 foot of uncoated copper wire at 14 gauge. Here we go. Go to row 14. You see this one? Boom. At 14 gauge is telling me that 1,000 feet of copper has a resistance of just over 3 ohms. That's ohms per 1,000 feet. Ohms per kilo feet. Ohms per 1,000 feet. So 1,000 foot of 14 gauge copper has resistance of about 3 ohms. How about 12 gauge? Just under 2 ohms. How about 10 gauge? Just over 1 ohm. You all see how they list that for you? So let's go back to our example. Now, let's just round them up. So let's say 14 gauge, 3 ohms per 1,000 foot. 12 gauge, 20 ohms per 1,000 foot. And 10 gauge is 1 ohm per 1,000 foot. Now, we have a light bulb here on this circuit. This one's an incandescent light bulb. They were really robust. They're just a piece of coil that you put electricity through and it'll glow in the dark. So If the wire is 14 gauge, let's say you do that, you put that circuit, you only have one light bulb in the garage, you're like 14 gauge is more than enough, I'm just run 14 to it. Table 8 just told us that you're putting 3 ohms on that 1,000 foot and 3 ohms on this, right? So you're adding 6 ohms of resistance to your total load. Your load is a 240 ohm incandescent light bulb. I'm not sure if they teach you the formula in this one or next pod, but George will give you examples of voltage drop calculations. Huh? You did that already? Okay. So if you do your calculations, you see that the voltage that that light bulb will see instead of 120 is 117. So about 3 volts has dropped from here to here because of the wires. Is that a big deal? 117? No. We call it 110 volt system sometimes, right? So who cares about 3? No big deal. But what if it wasn't a light bulb? What if I had a heater, a water heater, something low resistance, like a water heater or a heater, like this heater, if you had 20 ohm resistance, now look what you're adding. In the last example, 6 ohm compared to 240 ohms. That's 40 times more. So the voltage drop is very little. But here, 20 ohms versus 6 ohms. That's almost just over 3 times. So this becomes significant compared to that. And the way, and look, now you understand series and parallel. This wire is in series with this and in series with this, right? Remember your swamp bridges? Electrons that come through here have to go through that first, then this, then this. There's no parallel here. So our wire is actually is always in series with our equipment. But we usually ignore it because it's such a small resistance. But in longer distances, now we got to worry about it. So 1/3, what do you think is the voltage drop? It's going to be way bigger. So the voltage that this heater will see instead of 120 would be 92. Would that heater work with 92 volts? I don't know. If it's an old school, just an element, it might come on, not heat as much as it should. If it's got electronics and controls, perhaps it won't even come on. A lot of equipment that have control, they're designed for the system. What's our system? 120. We don't have a 92 volt system, so it won't come on. And that's why we have to worry about voltage drop. Now, what do we do to fix this? Upsize the wire, right? What does that mean? So we have 1,000 foot of 14 gauge. Let's replace it with 12 gauge. Now our resistance went down from 6 total to 4 ohms. 4 ohms compared to 20, now it's 1/5 instead of 1/3. So look what happens to your voltage. Jumps up to 100. So this one sees more of that voltage. Still not enough. What if we upsize to 10 gauge? It's 1 ohm for 1,000, so it's 2 ohm total. That's 1/10. And bam, we're at 110. I guarantee you, any system you put on 110 volts instead of 120, it works fine. Because that's the system. Sometimes we even call it 110. UL has a rule of thumb that it's usually about plus minus 5%. So in a 110, 120 system, it's like 115 plus or minus 5%. Everybody has to design their equipment to work within that range. But as soon as you fall outside that range, things stop working. So as electricians, you got to think ahead, right? You got to see things that others don't see and plan. Because if you run that 14 gauge, and then the builder, your homeowner calls you and hey, nothing's working in this garage. You come and fix it. Believe me, it costs a lot to rerun the wire as opposed to do a little calculation and say, you know what, it's going to cost. And you want to do that even before you do the bids or proposals, right? Because if we bid the job with a 14 gauge to every home with those garages on the other side of the yard, and then we figure out, no, we need to upsize, we'll have to eat the cost that comes out of our profit. But if you see that before, when the proposals are done, going to the builders, we're estimating the cost of the job, we give it to them, they pay us for it. So you have to keep these things in mind. Any questions on voltage drop? Everybody's clear? So yeah, go ahead. Okay, that's your voltage drop calculation. You did that, right? So all I'm saying is that that voltage drop calculation tells you that you'll have a 10-volt drop if that's the wire that you have. So 10-volt drop will get you, instead of 120, you'll see 110 at the end. But I can, if you guys are mathematical, this is a simple ratio. You can do it in your head. So it's not complex, but I don't want to give you guys multiple ways to solve things. You know how to calculate voltage drop, the examples that you did already, right? So that's the formula. You put in what's the current draw, what's the distance of the wire, what's this and that, and you get the voltage drop. So that formula gives you what drops from 120. So if you did the calculations for this circuit, you'll get 110. You get 10. Yeah, this is additional to teach you why it's happening, right? Now, your question is how to bring ohms and current. Like you need current for that one, right? So you want to see, you have ohms, how you can find current. That's a great question because it's exactly what we're talking about next. So Ohm's law is actually what allows us to figure out quantities, right? So Ohm's law. Ohm's law gives us the relationship between current, voltage, and resistance. These questions are really good. When I see you guys trying to get ahead of the lecture, that shows you're following. So we call it Ohm's law because it was George Ohm that came up with the law. And he was a brilliant man. Remember, this is long before 1827. We didn't even know what electrons are back in those days. So he figured out this relationship between current, voltage, and resistance before we even knew about electrons. Yeah, he was a bad speller too, right? Because he knew everything about math and physics and electricity, but he couldn't spell his own name, right? Yeah, he's German, and his name correct pronunciation is actually Georg, but we call him George. And he figured out that this is the Ohm's law. That current, can everybody see? That current equals to voltage divided by resistance. All through these talks and slides that we saw, you ever notice that for voltage we use V? Makes sense, right? For resistance we use R. Makes sense. But for current we use I, not C. Ever ask yourself why? This is where I comes from. Because the way he figured out this relationship, he actually had his assistant hold on to hot and neutral and started putting voltage on the line. And as he increased the voltage, he measured the intensity of the shock. So I stands for intensity. We like to say it's intensity of the current, but it's actually the shock that he was measuring. So I guess by the time he was at 480, he was probably jumping and crying, and he figured out, hey, as I increase, the resistance is the same. His body resistance is the same, right? Electrons are going through right through his heart too. OSHA was not around back in those days. He could do whatever he wanted to his assistant. He did himself too, but this was actually measured because you can't really be shocked. I mean, he did himself too, but it's the two of them. It's an interesting system that they work together. So as he increased the voltage, he kept the resistance the same person, and he noticed that the intensity of the shock was going up. So he figured out that voltage is directly proportional to the actual intensity of the current. And then he kept the voltage the same, let's say at 50 volts, and he changed the resistance. He noticed as he reduces the resistance, the shock goes up. So he figured out that it's inversely proportional to resistance, and he came up with this relationship. That's called Ohm's law. So back to our Resi example. So we have our breaker, circuit, light bulb. We already said our system is 120 volts, and we said that we had a 240 ohm incandescent light bulb on it. So let's see how he can use to figure out what's the current flowing through that. So you have the resistance, you have the voltage. Now you want to find out I, because you used current for your voltage drop formula, right? So this is how it works. Basically, you take R, we have 240, so replace that with 240. Then you have V, that's 120 volts, right? What's 120 divided by 240? It's 1/2, half an amp. That's the current that's flowing through that light bulb. So if you have voltage and resistance, you can find current. If you have voltage and current, you can find resistance. It's simple math. Now, can I use 14 gauge? So half an amp is really nothing. We already talked about copper. Let's say copper. On a 14 gauge copper, how many amps can I put? We talked about it earlier. 15. 15 amps, we can put the code table 31016 allows us to put 15 amps on copper. Half an amp is a lot less. I can put, 20 light bulbs on this circuit and I'll be at 10 amps. So is this code compliant? Can I use 14 gauge? Yes, no? Well, this is a trick question. The conductor size is sufficient for your load, but you cannot protect a 14 gauge with a 20 amp breaker. Always remember, there are some exceptions like ACs, motors, the code allows us to go over. But in general circuits, your breaker cannot be bigger than the wire. It has to be sized to protect. So this is a 15 amp max wire. You have to have a 15 amp breaker, because if it's a 20 amp breaker, you can draw 18 amps on the 14 gauge wire and the breaker will not trip. And 18 amps on a 14 gauge wire, resistance starts heating it up. Now we understand electrons moving. That's why the code has those numbers that we can't go over, because we'll heat up, burn the wire. This is why, and I'm not knocking any other trades. We are actually our HVAC and plumbing company now. In our Florida, our divisions do the whole thing. So, but as electricians, everybody here is for electrical training, right? Do we have anyone from Bayonet or other divisions that do plumbing, HVAC? No. So this is why it's so important for electricians, because as simple as that, you put the wrong breaker on the circuit, that house may go up in smokes. What happened in New York this week? Yep. How many people died? They haven't totaled it. A lot of people are in critical condition, but first reports was like 19 people dead. And what caused the fire? A space heater, I think, yeah. What we do determines safety of people. The home that you're wiring out there as a training crew, this is my mindset. Anytime I put my hands on wire devices, and when I'm actually tightening those screws, I'm thinking that my children, my nieces and nephews, someone's children will live in these rooms. If they go up in flame, they'll die. Keep that in mind every time you're tightening a screw, every time you have to torque a screw, and you will do it right, because our job matters. It's one of those critical industries that safety of people really depends on us. So yeah, what you have to do here is, 14 gauge is good, but we got to change our receptacle to a 15 amp receptacle, and that will protect the wire. So anytime You draw. If you try to pull more electrons here than 15 amps of current, boom, this one stops it. It's like, no, no, no. So it could be a short circuit. Remember short circuit where there's no big resistance? You connect the hot and neutral together. It'll try to draw more current and it'll trip the breaker. All right, so Ohm's law put these three quantities together. If you have two of them, you can find the other one. There's another rule that we call it the power law. This is very important. This one uses V, voltage and current, gives us power. And it's a simple straight multiplication of the two. So if we go back to our example, we said that we have a 120 volt system and we're drawing half an amp. So what's the power that this system is delivering, or how much power is that light bulb using? Just put the numbers in, right? Multiply those two, it's 60. What's the unit of power? Watts. So 60 watts. 60 watts sounds familiar? Anybody? Most famous light bulb of all time, right? For decades, that's what we used. Even today, we're using LEDs that use like 7 watts of power, but they say it's comparable to a 60 watt because our perception is still on those. So that's power. I'm going to add power to our list of quantities, so you'll remember this one. What is true power? And we use P for the symbol, but we have another unit for watt for power, and that's volt amp. It's easy to remember because power, the formula was voltage times current, right? So volts times amp. Volt amps gives us power. And as far as your wireman test is concerned, volt amps and wattage are the same. So you don't have to distinguish them at this point. But I'll tell you why we have two, because they're not really the same. And you can understand it because you understand the theory behind it now. We said that our power source in AC keeps flipping, right? So if the voltage and current flipped at exactly the same time in an ideal situation, volt amps and watts would be the same. The problem is it's not an ideal world, right? So when we flip the voltage, current takes a little time to flip. There's resistance and capacitance and inductance that we don't want to get into the details of, but the current doesn't flip exactly the same time. There's a little bit separation. This one goes first, then this one goes. Then this goes back, then this goes back. The longer that separation gets, the bigger the difference between VA and watts come to. Because VA is always the same, right? You're multiplying voltage and current. But because of their separation, the true power that you get will be different. So for wireman test, I want to maybe journeyman. I'm not sure. You might want to ask George if they ask you about power factor and all that in journeyman if you're taking that test. But for now, we assume they're the same. All right, so between these two formulas, anytime you have two of these quantities, you can find the other two. Those of you who are mathematical, it's math. It's easy, but we don't have to be. I'll do an example and then I'll show you how we have the... Have you used the Ohm's law wheel yet? No, okay. We'll go through it and then Jimmy and Luis will do a whole bunch of examples for you guys. So let's do a real example mathematically first. So this one is, let's say this one is Kyle's toaster. He's got a super toaster, 1200 watt. That's a mean toaster. If you get a 1200 watt toaster, you can probably toast your bread in 3-4 seconds. That's usually the wattage that microwaves have these days. But let's assume, for simplicity, we want the numbers to be rounded. The question is, you can look at the back of your toaster and it tells you it's 120 volts. So can I use this in Europe? Not without a transformer. I have to convert. Europe is on 220 system. We're on 120. So this is a North American toaster. 120 volt is our system. And it's telling you the power that it uses to toast the bread is 1200 watts. Question is, how much current is it drawing? So what are we given here, guys? Voltage and what? And power, right? We have voltage and power. And what are we looking for? Current. So let's start substituting numbers. You put the numbers, and what do you get for I? It's going to be 1200 divided by 120, 10 amps. 10 amps is the current that this system is drawing. Now, I figured out we're drawing 10 amps. Kyle wants to know what's the resistance of his toaster. So we know the system's 120, 10 amps. We start putting 124 volts, 10 amps, and we see that we get R equals to 12 ohms. That's the mathematical way. If you don't want to deal with formulas and cross multiplication and solving equations, that's where the Ohm's law will come in. This is given to you on the cheat sheet for all your tests, even master's tests, they still put this on it. So you don't have to memorize any of the formulas, and you don't have to do the math part, the complex math. Let's see how we use the Ohm's law wheel to figure out. So I said that between these two formulas, or by using the Ohm's law wheel, if you have any two of these quantities, you can figure out the other two. The way I use my Ohm's law wheel, I only have two questions every time I come across an Ohm's law problem. First question is, what am I looking for? You got to pick the quantity that you are looking for. And then next question is, what am I given? I said you have to have two out of those four items to find the other two, right? If you have three of them, you can just pick two of them, and that will give you the other one. If you have only one, good luck. There's no way you can solve that equation with only one known quantity. So how do we use the Ohm's law wheel? So question one, what am I looking for? So out of these four quantities, current, voltage, resistance, and power, I'm usually looking for one, right? Answer of this question is, I'll go to the inner circle. So which one am I looking for? Current, voltage, power, or resistance? Inner circle. Question two, and this one determines which quarter. So if I'm looking for I, if I need to find I, that's the quarter that the formula resides in. If I was looking for voltage, it'd be the second quarter. Resistance, I would look at the third quarter, power the fourth. So then I have to see, what am I given, right? We said we got to have two of these. So let's look at an example. I'm looking for I, and I'm given voltage and resistance. Now I look at the outer circle. So I pick the quarter. I'm looking for I, so that's the quarter I want to be in. Then what am I given? Voltage and resistor. Which one of these formulas has voltage and resistance? Bottom one, right? So it tells you all you have to do is plug your numbers. Voltage divided by resistance gives you I. Let's do another one. Let's say I'm still looking for I, and I'm given power and voltage. So when I look at the quarter, I'm looking for I, so that's my quarter. Which formula do I use? I'm looking for P and V, the middle one, right? So that gives it to me. All right, let's do an example for you guys. Let's say I'm looking for R, and I'm given power and voltage. So I'm looking for R. Where do I look? Inner circle, that's my quarter, right? Because I'm looking for R. Always locate what you're looking for in the inner circle. That's my quarter. Now I'm given power and voltage. So which formula? Middle one, right. So that's how you locate the formula. Now, this one has square. This is the last item that I want to talk about. Square and square root. Some of these formulas have that. You might remember them from your high school math, but we'll look at it again. Good news is it's on your calculator, so Jimmy and George show you how to do it. But I personally like to know what am I doing on the calculator. With square root and squared, all you have to do is remember this, that 3 squared is 9. Square means something multiplied by itself gave you that number. What does it give you? So when we say 3 squared, means 3 times 3 is 9. What's 2 squared? 4. What's 6 squared? What? 36. 36. Now, square root is the opposite. Again, all you have to remember is this. 3 squared is 9. Square root of 9 is 3. So when you see square root, it's saying what number was multiplied by itself that gave you this. So when I see 9, I'm asking what number was multiplied by itself to give me 9? 3. So technically, this is all you need to remember for the rest of your life. And anytime you come across square root or square and you don't remember, just remember 3 squared is 9. So square root of 9 is 3. That's all you have to remember. But both of them are on your calculators. These calculators are allowed in your basic electrician, wireman test, journeyman test, master's test. So we'll, once you do the actual examples with the guys, you'll see how to do the full calculation. That covers all the topics that we wanted to talk about today. We went over basic quantities and definition of AC, DC. We looked at series and parallel. Remember your bridges. That will tell you anytime you forget. Voltage drop. Remember what resistance did to our wires. When they get long, resistance goes up. So we start worrying about actual voltage drop over long distances of wire. We looked at Ohm's law, which brings the quantities together, right? Ohm's law was current and resistance and voltage, and then we looked at power law, which was current times voltage gives us power. Between all these equations, you can solve any Ohm's law related question. You can figure out power and current and voltage on all your test questions. But in general, on all the concepts that we talked about, was there anything that's confusing to you? Anything that we need to clarify? Remember, this is it. Once you're out there, whatever your position is with the company, it gets harder to have access to information. You can always pick up the phone, call George, call me, call Jimmy, Jason, whoever, but you get engaged. So this is the time you're here. Take advantage. Make sure you don't let anything go by without fully understanding. I'll be in and out for, you guys can call me, text me, email me if you have any questions. They have my contact information here. So if you guys come across any issues, any questions, get in touch with us. Don't let it go by. We want you guys to be the ambassadors of our company. Not everybody. We have 3,200 employees, I think, now. So only a portion of our entire workforce gets to go through all these pods and get the full training. So we want you guys to be ambassadors. When you leave, help people understand, be the go-to person in terms of questions, really learn as much as you can at every stage. And, with safety, electrical theory, code, help others understand the code and, learn it as good as we can. Right. Well, typically, the resistance of a wire is small enough in short distances that we can ignore it. Now, it also depends. We're talking about our trade, right? We're residential electricians. We're looking at residential wiring. In some sensitive industrial equipment, even at a 10-foot long, you have to worry about voltage drop, voltage regulators are loose. Some systems are very sensitive. But for lights and devices and motors and things that we use in residential setup, usually short distance is resistance not big enough to worry about. Anything else? All right, that's great. Well, what time is it right now? I think it might be close to your lunch break, so we're going to take a break. They'll tell you. I don't see any of your instructors, so they'll tell you if it's lunch or they're going to do something else. But good luck to you guys all. If you do multifamily, if you go that side, I'll see you guys in multifamily pods as well. But remember, this is our favorite place to be. So anytime you guys have a question, get with George, get with me. We're always there to help out. All right? Best of luck. Can't wait to see which one of you guys make it to division manager level first. All right. Good stuff. Thank you.